I should have used the word pathological in the title, now that I think about it. But it'll be pathological design features that can ruin your day. So that's going to be the keynote. In fact, if it's not, now that I think about it, maybe I will try to grab Judy and change the title to pathological design features. But it's going to be really bad design guidelines. Don't do this in your design.
Thank you, everyone, for joining us, and welcome to the OnTrack podcast. I am here with Dr. Eric Bogatin, who is a well-known speaker at many Altium Lives and in many other outlets within the industry. I think I first saw Dr. Bogatin speak at PCB West 2019, and it was a very enlightening discussion. He threw lots of pieces of candy at me after answering his questions. So definitely a great person to go out and see speak if you have an opportunity.
Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media.
Dr. Bogatin, thank you so much for joining us on the podcast.
Hey, Zach, it's always a pleasure to join you guys on your podcasts.
Well, I will do my best to commandeer this thing until Judy gets back. She is busy planning Altium Live at the moment, and I know that you are going to be speaking at Altium Live again this year. I was watching your... Just recently, I was watching your talk from Altium Live 2020, the virtual session, and very cool stuff, obviously. So I'm interested to hear about what you're going to talk about in this coming Altium Live.
Yeah, so let's see. So I think I'm going to do two presentations. One is, so I always enjoy coming to Altium Live when it's been live, and then even when it was virtual, because it's such a great opportunity to be around enthusiastic users of Altium tools. So it's a very friendly, very good audience to participate with. Let's see, I think I'm going to do a keynote on something about how noisy designs can be if you're not careful in the design guidelines. And I always say that if you look at a schematic tells you about how the terminals are connected and what components you've got there. But when you translate the schematic to a layout, the schematic doesn't tell you anything about how the interconnects themselves behave. And so when you create the layout from the schematic, that's when you have to pay a lot of attention to the role interconnects play in the system. And interconnects will only screw things up. They will only introduce noise. They can never improve the performance of what the ICs and the active devices can do. And so it's really about, interconnect design and the layout is really about what can you do to reduce the noise. And I'm going to look at or demonstrate a couple of what I come across as the most common sources of noise where you can have so much noise it will break your system. And I think one of them is going to be I'll probably show off some ground balance examples, because ground balance can grow because of the shorter rise times, the more IOs that switch. You can easily see ground balance in the volt kind of range. And then I'm probably going to look at near field emissions from a good and bad design that can contribute to FCC certification, EMC failures. So that'll be about some extreme, maybe I should have used the word pathological in the title, now that I think about it. But it'll be pathological design features that can ruin your day. So that's going to be the keynote. In fact, if it's not, now that I think about it, maybe I will try to grab Judy and change the title to pathological design features. But it's going to be really bad design guidelines. Don't do this in your design. And then I'm doing another technical session to walk through how to use the built-in 2D field solver in Altium in order to do stack-up design, because it's a really cool feature. I use it all the time. I make my students use it. Really easy to use, and I think it's a really powerful addition to Altium Designer that I think more engineers should know about.
Yeah, I definitely agree about the layer stack manager. I use that tool all the time. One of the designers that works for me uses Polar as well. And so we, if the client demands Polar and that we use Polar and, go with their results, that's fine. But we generally use the Altium tool. I think it's the best.
Yeah, Polar they have a great 2D field solver tool. I feature that a lot in the last book I did with Artec on transmission lines. Really easy to use. You can do a lot of stuff with it. If you don't have Polar, I think more Altium users should know that there is a really good 2D field solver built in for free in Altium, and that should get more visibility, more usage.
Yeah, it's funny because, like you said, it's in there. It's not like it's hard to find. There's a little tab at the bottom that says impedance. But one of the questions that I see sometimes is, well, how do I figure out, if I change the width and I don't know intuitively what I need to do to the stack up to accommodate that? Where do I figure that out? Is there a tool in Altium? And then, I'm always replying with links. Well, go learn about the layer stack manager.
Yeah. And you said the key thing is, you have to have some intuition. I think it's important to have that intuition about what do you expect. If the alignment gets wider, what's going to happen to the characteristic impedance?
Exactly.
And so if you're not familiar with characteristic impedance and how the geometry affects it, it's hard to have that intuition. But I think before you use the stack-up tool or any other tools, you should have a little bit of that physical intuition of how design is going to affect performance, and then you use the tool to put in the numbers to give you that couple decimals to do the actual optimized design.
Yeah, I totally agree with you. I think that if someone just kind of jumps in and they don't, it's as simple as changing a number, right? You're changing a laminate thickness, or you're changing a width. Maybe you're changing the copper weight. But let's say you go to change the laminar thickness. If you change it the wrong direction and you don't have that intuition, you're going to start thinking, well, what's wrong with this tool? Or does everything I know, does that mean everything I know is wrong? And, that's...
Yeah. Or maybe you're, typing in 17, you meant 71. You didn't notice that. I'd make that mistake. And so the number comes out. And if, it's so many of these tools, I always say, it's really easy to get a number. It's hard to get a number without artifacts. And having that idea of what to expect, that's what I call rule number 9. Having that anticipation of what to expect is such an important check on how you're using a tool.
Yeah, I totally agree with you. When you brought up the most common sources of noise, you brought up two good ones, which was ground bounce and then EMI. And I was going to say the third one that you were going to bring up was crosstalk. Are you also going to show some interesting results with crosstalk? Because I remember in one of your sessions, students designed like a little 555 timer, and you encourage them to do design less than optimal, let's just say. And you can see the crosstalk on a blinking LED. Are you going to show some more results with that?
Yeah. So I kind of lump crosstalk as an extreme case. Ground bounce as an extreme case of crosstalk. So if you and I'll tell you the punchline. It's return path discontinuities. Mm-hmm. So if you have a nice wide uniform plane, you won't see ground bounce at the board level. You'll see it in the packages and connectors, but not necessarily at the board level. But if you screw up that return plane, then you see it at the board level. And it can literally be orders of magnitude increase in noise. So we'll definitely be talking about crosstalk. When you look at the different sources of noise that interconnects can create, some of them are based on reflection noise and terminations and that kind of thing. Crosstalk, and then the rise time degradation because of the losses in the lines and jitter and collapse of the eye. And then the fourth is EMI. And so I was only going to hit the big ones, the real serious pathological ones, ground bounce, which is extreme crosstalk, and then design structures that can strongly contribute to EMI failures.
Sure. Yeah, I think these are all really important important topics within really at all levels of a design, but especially when you're starting to deal with designers who maybe have different levels of experience. So, the new designers, this is something that I think in the past was kind of at the edge. It was something you dealt with as an exception and not the norm. And then now, with even so many simpler devices running at edge rates that are fast enough to produce some of these problems, it is now the norm. And so I'm wondering if you get a sense, or if you have some experience working with students possibly who have experienced these problems, and then they're just unsure of what to make of it until they, maybe interact with you.
Yeah, so that's a really good point. That I get, so I teach it's an upper division and graduate class on printed circuit board design, and I get students that, so at CU we're pretty heavily into projects. Students get involved in building things early on. Freshman year, there's a project design class. I'm teaching the senior design class right now, and throughout their curriculum, they'll often get involved in projects, and sometimes they'll do printed circuit boards. And so I'll get students in my class that have maybe built a board or two, or they've seen boards, and it is remarkable. And I know that none of the Altium professional users out there would ever do this, but my students that don't have a lot of experience, they haven't gotten feedback on the designs, they just naively design a board. The vast majority, they just naively design a board with no ground. The vast majority, it's literally taking a design that you would have in a solderless breadboard with connections and wires going everywhere, and implementing that in a printed circuit board. And for a lot of the simple designs that they do, it works because the interconnects are transparent. And so I try in my PCB class, I teach them the good habits, but I also try to get them involved in circuits where the interconnects are not transparent. And you exactly mentioned it. The example that I show, yeah.
Real quick, when you say transparent interconnect, I assume you mean electrically short.
Well, electrically short is part of it. That just means it doesn't behave like a transmission line, but it's also doesn't the noise that you get, because the inductance in the leads, the rail collapse, the IDT, the noise that you get doesn't depend on the interconnects. You can literally, and my rule of thumb is, if you can build your product in a solderless breadboard with jumper wires and it works just fine, the interconnects are transparent. Doesn't matter how you design the circuit board. And generally that's how a lot of these students have built their boards. They've never gotten the feedback, they've never gotten the experience of what happens if interconnects are not transparent, if the design of the interconnects influences the noise. Yeah.
So I'm assuming you're dealing with students who are at least able to route in such a way that they're not going to break an interconnect that was already made with just a wire.
Exactly. I mean, you start with a schematic and you push it over to the layout and you get all the ghost wires there. And my students are used to using simpler tools and just doing connectivity, just wires to go to make sure you don't have any ghost wires left anymore. And those designs have worked for them, but it's bad habits, number one, and number two, they will absolutely have a design in one of the next ones they do where that doesn't work. They have a microcontroller on their board, or they have any kind of high current drivers. Then that simple just connect the dots with wires isn't necessarily going to work. And so I try to establish good habits, and then the second board that they do is a board where they route one quadrant just with wires with no ground plane, and then identical circuit with a quadrant where there's a nice return plane. They use good design habits, and they actually get to measure the crosstalk noise when they don't pay attention, and then how much it's reduced when they do pay attention. And it's that
I see. So they've got a direct comparison on the exact
and
same board.
It's a combination of, I also try to teach best measurement practices, because I think it's important for hardware engineers to know how to measure correctly, but they see that visceral sense of, oh my gosh, it's exactly the same circuit. The only difference is how I did the routing, and I can reduce the noise by a factor of almost 10 in some cases by doing the routing correctly. And we use hex inverters with only a couple, maybe one or two nanosecond rise times, which common these days. An Arduino board has a Atmega 328 microcontroller in it. That board that's been around forever. I heard from the microchip guys, over 1 million of them are sold each year. The actual board itself, the Uno form factor. You can buy them clones for like $3. That board, 3 nanosecond rise times. In some cases, a little less than 3 nanoseconds. Pretty fast edges, and you can see a lot of crosstalk on those boards.
Yeah. Yeah, that's interesting because I think there's this perception that something like Arduino or maybe another microcontroller board, it's going to be one of those things where it's supposed to be simple. So why would you have to worry about these things that seem really advanced or really complex? But I think it just underscores that issue where those things actually are the norm, even in something that is supposed to be like a beginner's product, like an Arduino.
Yeah.
And I think for many designers, that definitely is the beginner.
Yeah, you're absolutely right. I mean, we also build a Arduino board as one of the test boards, and we compare it to the commercially available boards. And if you look at the commercial available boards, and that's one of the exercises we do, is I have them, once they understand what the good design practices are, we look at one of the commercial Arduino boards, and I have them make a list of 5 things they're doing wrong. And then we compare the noise on the commercial board with the noise on their board that they've done correctly. And the biggest difference, surprisingly, is, so bottom line is, look, the Arduino is an incredibly robust design. It's a 5-volt logic. It tolerates a lot of noise. But if you know how to measure it, you'll see a lot of noise on the board, but it still works. But surprisingly, the biggest difference between the commercial board and the board they build is from the emissions. And I'm going to show this at in Altium Live, that the commercial boards, because they use split planes all over the place and they use copper fill everywhere, they think they're doing a good thing by using copper fill, but they're not careful in how they do the return path control. And there's more than an order of magnitude difference in the near field emissions from the commercial board than the ones my students build with nice continuous planes. The near field emissions are a factor so low, we literally are at the limit of our poor little scopes to be able to measure it. Can't measure the near field emissions on the boards the students make. So there's a very visceral difference.
Yeah, it's amazing. The thing with split planes, routing between plane sections. I mean, I don't know when that started. And I have heard from, I don't want to say older guys, but I will say much more experienced folks in the industry, that this is something that was totally fine, like pre-1980s, something like this, way back when, before I was even alive. And so it's just interesting to me that something that, like you're saying, you can measure that it doesn't work, is still pushed as like a standard design guideline, including when you're dealing with something like the mixed signal, and people still do it. I even see, running a design firm, I even get clients that will send in something to me for rework because it failed EMI, and it failed. And what do you think the first thing I look for is?
Split planes.
Split planes, yeah. Split planes are crossing references without providing a continuous return path, but it's basically the same thing.
You're absolutely right. I think signals crossing planes, return planes, are I call it the trifecta. That you get reflection noise, you get crosstalk noise, you get EMI noise out of it.
Yeah, absolutely. Yeah, that's funny. And I even see it in app notes.
Yeah.
Yeah, I still see it in app notes. And these aren't app notes from, 1990. They're app notes from like 2008. So
you must see a lot of designs come through your firm then, if you get clients from outside sending you designs to fix or to start originally.
Well, it's not a huge number, but yeah, we do occasionally get the get the request for rework for EMI, EMC problems. And like I said, that's usually one of them. Or they will do something weird where they try and tie planes together like with an inductor and then use that as a return path. Not an inductor, but a ferrite, basically. An inductor. And you already know what I'm talking about. And then they'll do something like, oh, well, we want to be able to provide a low frequency connect, or we want to eliminate the DC blocking between them, or we want to provide a high frequency return path. And so then they'll put a capacitor in parallel with it. So they've just created an LC tank. And then they wonder why they're seeing this huge spike in their EMI spectrum. And, it's little stuff like that where it's just like, if you would have just used the continuous return plane to begin with, we wouldn't be having these problems. But with dealing with EMI failures, and this kind of relates to something that you brought up in terms of like using copper poor instead of ground planes, it seems like some of these recommendations are sometimes recommended either as a Band-Aid for a problem when they should be dealing with the cause first, or it's just one of those things where it's like, well, I see everybody else doing it, so Zach, will you guys please do it? Do you see students maybe providing the same type of justification for certain design practices? I mean, whether or not it's copper pour or stitching vias or guard traces, I still see people recommend like guard traces, this kind of thing.
Yeah, I think you're absolutely right. It's a combination of myths and legends that have stayed in our industry, or legacy code. And I see, you mentioned one of the real common examples of the use of guard traces. My other two favorite ones are the use of copper pour on layers that have signals on them, and the third one is I call it the myth of 3 capacitor values. That
was my favorite.
Yeah, that was such a prevalent comment and there was, I think, of all the habits my students had coming in, the one that they learned from either app notes or they learned it from other professionals in the industry, or I have some students that work full time and they learn it from their design community, and they see it in app notes, is the idea of using 3 different value decoupling capacitors of a 10, a 1, and a 0.1 microfarad. And so I have had classes where I show examples and I talk about the principles behind it, and I still get students that do it because they said, well, that's what's in the app note. And so about, I think it was 1 or 2 years ago, I got together with Larry Smith is kind of one of my go-to experts in the industry of power integrity. He and I wrote a book together, and I spent 5 years once a week for 2 hours on the phone with him, going through all the material and arguing a lot and discussing it. He won most of the arguments, but we both still learn a lot from it. So he's one of my experts. And then Steve Sandler, another industry expert in power integrity, very, very sharp guy. Sometimes he assumes that everybody understands things as well as he does. And so sometimes it's a little hard for me to understand exactly what he's telling me, but he's usually right. And so the 3 of us, I got them together and we had long discussions about the myth of 3 capacitor values, and we did some investigation as to where that myth came from, where it started, why it is appropriate in some cases, and then we came to our own conclusions about that it's not appropriate in modern designs. And we wrote an article in Signal Integrity Journal a couple of years ago. Anybody can go to signalintegrityjournal.com and just do a search for myth of 3 capacitors. And if you still design with 3 capacitors, I strongly recommend you grab that, copy that article, and we walked through where the myth came from, when is it appropriate, and when is it not appropriate. And it's
that's a great point. We're going to link to that article in the show notes, so everybody who's interested in that article, go check out the show notes and take a look.
It was a lot of fun working on that paper. We also had a lot of arguments when you get 3 experts together and you probably have 4 different opinions about things. So, but I like doing that every now and then because, I find even when I teach a class I've taught for 20 times, I still learn something new when I teach it, or when there's someone in the audience that challenges me or offers some other view. And so with guys like Larry and Steve, they're so opinionated about what they do, and they each touch a different piece of the elephant. They have different kinds of designs they work on, and so the generalizations and guidelines for one design don't always apply to another, and that helps us challenge our assumptions and we rethink. So it's always a lot of fun. I always learn a lot when I work with other experts with other perspectives.
Yeah, I love that you said that. The generalizations. I think that's what gets a lot of newer designers, is a generalization of one design guideline that works fine in one specific case, but then they want to apply it to every other case. And I think if there's a lot of context that surrounds some of those guidelines that often gets lost, especially if you start doing searches online, looking on forums, and then you start seeing discussions. Sometimes you'll see discussions around this stuff where one guy says, well, I always do this and I never have a problem. And then the next guy says, well, I never do it and I never have a problem. Well, who's right? They're probably both right. It's just that the situations are totally different, and then we lose all of that context.
Very good.
So I think it's great that you can get into that. And, that's one of the things that I think we try and do in the articles that get posted on Altium's blog. But, I see you doing that as well in a lot of the stuff that you create, especially on Signal Integrity Journal.
Yeah, and it's this question about it. I did it and it worked. I often say sometimes working isn't the same as margin, and if you haven't looked at like I said, the only thing interconnects are going to do is introduce noise, and if you haven't looked at the noise, it may not be enough to cause the product to not work, but it could still have significant amount of noise that may be close to the edge, and so just because you did something and it worked doesn't mean it worked because of what you did. It could be working in spite of what you did. And that's why it's so important to, like you said, go back to the fundamental principles and try to quantify, try to measure the impact of the noise that you have, even if it's not enough to cause an actual problem.
Yeah, what you're really saying is that, it would have worked anyways, you just didn't break it.
Right. And, I remember a story, I think Istvan Novak told me this. We worked at Sun years ago, and this was in the early days. So Larry Smith and Istvan both worked at Sun and worked very closely together, and really pioneered in a lot of the design principles for power integrity. And I was running the processor modules group, and there was a story I think it was Istvan told, that they had built a server board with some of the modules that my group was creating. With some of the modules on there, and they wanted to, and there were like 1,000 decoupling capacitors on the board, and they wanted to know how many decoupling capacitors did they need. And so naively, they started taking the capacitors off, and did it boot up? And darned if it didn't keep booting up, and it kept working even though they took off 999 of the decoupling capacitors. And so the conclusion, it wasn't Istvan's conclusion, he was telling the story, but the conclusion of the engineers that were taking the capacitor off was, we don't really need decoupling capacitors. And part of it was the modules that had the processors on them, we had decoupling capacitors, so that helped the noise on the processors. But the other is, there's a difference between, it goes back to the question of what does it mean to work? If it boots up, that doesn't necessarily mean it's going to work when you're running real code and you're running 5 different applications at the same time. And so it may work initially or in a very limited case, but it doesn't mean it's a robust design. And oftentimes, design products for not necessarily worst case, but cases that are extreme cases that could reasonably occur. And you have to have the right test vectors in order to have confidence that this product is going to work under typical kind of customer applications.
Yeah, it sounds like there was not a very good definition of success there.
Right, exactly.
Right, if your measure of success is, it turns on.
And it boots up.
Okay.
And because that's not necessarily the worst case. And I am, you're old enough to remember the blue screen of death that we would get sometimes with some of the old processor boards and running Microsoft Office. I am convinced that a lot of those problems were PDN problems that were worst case, because it was only when you're driving just the right combination of applications, when they all happen to be doing something at the same time, it was very unreproducible, and it happened only periodically. But typically, it was when you were doing a number of things in parallel. I think it's just the right combination of code is really, really hard to reproduce, but you have to stress the product under test in order to see that kind of behavior.
I never would have considered that, but it sounds like I'm going to have to go into my mom's garage and
okay, so here's my other theory of, because I see a lot of products. My TV will hang up sometimes. Everything has a microcontroller in it these days, and every now and then I will see like the TV, or I'll see a laptop, or not a Apple, but other phones. They'll lock up, and I think a lot of these problems are 2-bit errors, because so many of our products in communications paths, we do parity checks all the time in data sets, and so we can detect single-bit errors really well. The probability of a 2-bit, the probability of a 1-bit error is low. Probability of a 2-bit error in a packet is really low. But with so many products and so many hours being on, I think a lot of times when things hang up and they stop working, I think it's because it encountered a 2-bit error that changed a register value somewhere, and suddenly it's off in Never Never Land, or it's trying to execute some other command, or it's waiting for something that's never going to arrive. And that's why if you turn the product off and on again, it works. And because you're resetting to the default register state. So I think
Right.
there's a lot of 2-bit errors going on that if we could only, really hard to detect, but if we only looked for them, we might find them more often.
And so your contention would be this is a noise problem related to signal integrity, just from
Signal
bad board
integrity,
design.
or something else going on, and bad connector.
Or power integrity
Yeah,
becoming
yeah.
signal
But it's
integrity.
some
Yeah.
source of noise that could be cosmic ray too. I mean, I've seen a couple of reports of our electronic, unless it's rad hard, our electronics is sensitive to cosmic ray, or muons, I guess, coming in flipping bits. And if you get 2 bits flipped by some burst, I think that will create an error that's really hard to detect and hard to correct for.
Yeah, you brought up rad hard. I was actually talking with someone who works at a certain commercial space company, and yeah, he said he had to learn about all of this stuff with rad hard and how to make designs more reliable. And I think it goes into this whole other area of reliability that
Yeah,
most designers
right,
might never
right.
experience.
We have a program here at CU. CU is very big in aerospace. We have a large aerospace department and do a lot of. In fact, right now today, we have an organization, the Laboratory for Atmospheric Space Physics, and right now today, every single planet in our solar system either has a CU instrument orbiting around it, or on the surface, or has just passed by. So we do a lot of
Yeah.
space science stuff, a lot of aerospace stuff, and we have a program for undergraduates to build cube satellites. Our Space Grant Consortium. And so I've been talking with a number of student groups that are building electronic circuit boards for space applications, and that's one of the issues, is it's got to be really reliable. And these are skills that are very different from building a laptop, or a little IoT sensor node that's going to go on your balcony to tell you what the weather's like. These space rated, they're not man rated, but they're space rated products are a different set of design requirements that are needed.
Yeah, and speaking of high reliability, we're actually hoping to have someone from an aerospace company come on the podcast in the coming weeks and talk to us about that type of thing, seeing as how commercial space is becoming such a
Yeah.
huge area of technology just
Yeah.
recently. driven. I'm not sure what the big catalyst is. I think it's just so much money sloshing around in the system, and Elon Musk.
Well, speaking
Those
speaking of
guys.
Elon Musk, and I mean this in the nicest way, I think the other place that I'm really worried about reliability, maybe software more than electronics, autonomous vehicles. That
Oh, absolutely. Yeah.
I heard a talk Todd Hubing gave, and you might grab him and get him on your show here. Um, he talked about how do you evaluate the reliability of automotive electronics, and he said that there right now today there are 30 people killed each day in car accidents, and 99% of the time the root cause of the accident is considered human error, driver error. And so he says, when we start having more autonomous vehicles, then we're not going to have the human error to blame anymore. And are we going to have 33 deaths a day? And how many, if we have one death because of an autonomous vehicle, that creates an alarm. And oh my gosh, someone was killed. Autonomous. 33 people are killed every day because of human drivers. And if we have autonomous, we can't blame the driver. Are we going to be seeing a lot of electronic failures or software failures because of that? So reliability is going to be increasingly more important topic for automotive systems, I think.
Yeah, and just this past year, we've been asked to clone a number of radar reference designs for some startups that are working on unique radar for vehicles. And the EMI concerns are usually at the end of it. I think part of that is because, reference designs try and make it really easy to just design something, not really design something that's going to be ultra reliable or ultra EMI immune or zero noise, but just to get you started and get you going and to buy their product. So it's good and it's bad. It's good if you're getting into a new area. It's bad if you're going to start relying on it as a production grade system. But and we've been guilty of this, and I think a lot of folks in the automotive industry are guilty of this. Is the EMI considerations are kind of at the back end and not at the front end. So I agree with you. Once you start having autonomous vehicles, and there is that risk of electrical failure and finding who do we blame for those deaths. It's going to fall on the EMI reliability, all of those areas of the design.
Yeah, I think you're right. I think EMI is going to be a big issue, and it's not just the EMI, but the susceptibility as well from all of the rest of the electrical systems, especially the electric vehicles. You get some pretty large current transients in there.
Yeah, well, maybe everything will go fiber in vehicle, and you can eliminate a lot of those problems. There's actually been some studies on it. I did a paper on it for a magazine, and there are people who are looking at fiber in vehicle and fiber-based radar. Interesting.
I think it's all going to come back to the cost, and
of course.
There are 6 or 7 cameras distributed around a lot of the autonomous vehicles now, or especially the EV cars, even though they're not autonomous, and they're all the data rates for the camera feeds are all raw data. So there's no encryption in them. So there's a lot of high-speed signals floating around throughout the body of the car. And you're right, going fiber would certainly eliminate a lot of the interference issues on those signals, especially if they're used to make intelligent decisions. You don't want glitches coming up or distortion. So maybe there is an argument for more fiber communication links in a car.
Yeah, well, I mean, with fiber, one of the bottlenecks is just the size of those transceivers and getting the fiber to go from an electrical signal to an optical signal. And that's where an area where I'm passionate about, I hope will receive a lot more attention, which is silicon photonics. Maybe that will be part of the solution, or EPICs, electronic photonic integrated circuits. So you can have photonic interconnects connecting to the chip. You have an electrical interface that can take that data in from a vision system, like a camera, like LiDAR, even if it's radar vision, whatever it may be. And then you can send the data around a vehicle with fiber. So I don't know, futuristic, visionary type of stuff, but it does fit in with the reliability and noise problems that I think you rightfully pointed out may be problematic for future technologies like autonomous vehicles. So we've got a few minutes left. What I definitely want to do right now is tell everyone to go register for Altium Live right now. If you haven't, you'll have a chance to see Eric Bogatin in person and hear some of his very enlightening talks. Definitely going to be very interesting. But there's one last thing I want to ask you, and it's probably going to be like dropping a nuclear bomb on the podcast. But there's one last thing I want to ask you, because I want to try and ask all of the very experienced designers this, because it is controversial. What do you think about right angle traces?
Okay, so actually, so at Signal Integrity Journal, we've had a series of articles about this. So the quick answer is folks should go to the SI Journal and type in, I think, corners or right angle bends, and you'll see a series of articles we've had. So the bottom line is, first question is, do 90-degree bends cause signal integrity issues? Or I have to get the right word. Do right angle bends cause reflections? And the answer is absolutely. We can predict them, we can estimate them, but we can measure them really easily. The second question is it a problem? And the answer is, unless you're dealing into the 56 gigabits NRZ signals, probably not a problem to worry about. But very noticeable. And we do one of the examples in our class. We have the students build boards with straight lines, with 90-degree bends, and with rounded corners. We have a TDR, and they get to measure them. And then they do an estimate beforehand of what they expect the impact of the corner to be. We estimate the capacitance, and we measure it from the TDR. And darned if they aren't within about 20 or 30% of each other. And that means once you know how to predict it, you can scale it down. And you can ask, okay, when I go to a really narrow line, 50 ohm narrow line, what's going to be the impact of the capacitance in the corner? And it comes out to, 5 mil wide line, you'll have about 20 femtofarads of capacitance. And now you can ask the question, is 20 femtofarads of excess capacitance an important problem in my design? And if the answer is yes, worry about corners. If the answer is no, go on to more important problems. So, but SI Journal is the place to find a series of articles that we've posted there. And
very great point. So it sounds like it's just an effective return.
It's a question of how much reflection will you get, and how much is important. But while we're talking about resources, so I'm going to do one other plug as well. So
go for it.
This topic of what do you worry about and why, and you brought up the point of it's not enough to have a guideline. It's important to understand the underlying assumptions for it so that you can know when to apply those generalizations. So I cover a lot of that in some of the courses that I've taught, and we've taken all those courses, we recorded them, we've posted on what we call the Teledyne LaCroix Signal Integrity Academy, and normally it's a subscription fee, but for Altium listeners and for your viewers, and we'll do this at Altium Live as well, special offer. Operators are standing by. Anybody interested in getting a free subscription, a 3-month subscription to the SI Academy, you just go to the bethesignal.com, you select the 3-month subscription, you fill a little form, and there's a place for a promo code, and the promo code to type in is ALT21, so Altium ALT21. You type that in, and you'll get a 3-month free subscription to the SI Academy. You can view all of the live lectures that I used to do that are recorded, and I have a whole section there about discontinuities and corners, and when do you worry about reflections from corners. So just want to offer that that little plug for all of our Altium viewers out there.
Absolutely, absolutely. Thank you so much. I'm definitely going to check it out myself, and I hope the listeners who are interested in some of the more advanced aspects of signal integrity will check it out as well. Well, thank you so much for being here, Dr. Bogatin. It's always a pleasure. We haven't talked a lot, but let's talk more. I have an article I owe you for Signal Integrity Journal.
We look forward to that.
Absolutely.
Hey,
thank you so much.
Great chatting with you, Zach, and look forward to seeing you at Altium Live.
Thank you. Yes, I'll see you there too. And to all the listeners out there, don't stop learning and stay on track.